Machine Chillers Incorporated has developed a new vortex tube-based cooling system that uses air as its working fluid. Burdell Incorporated has been tasked with the responsibility to review the entire system by modeling and determining its capabilities. There exist 5 measurement locations across the model that measure both temperature and pressure. These locations are spaced out to follow the air through the compressed air source, heat exchanger, vortex tube, cold and hot outputs, internal heat exchanger, and air output. The first week of lab focused on characterizing the steady-state relations, while the second week will focus more on the transient response of the system.
The methods in the lab are meant to achieve the goal of the characterization of the compressor, the vortex tube, and the heat transfer of an aluminum block, otherwise known as the load. Thus, a system consisting of these elements, a variety of sensors, and a network of tubing was constructed. To get the data, various temperatures and pressures were measured at different points, and so was the flow rate. Initially, the compressed air was supplied by the building via an air line, which allowed for a constant and easily measured flow. This allowed for the characterization of the vortex tube at different pressures between 0 and 80 nominal psi. Then, the compressed air input was switched to an engine-powered compressor. Similar data was obtained, along with additional data like the RPM of the engine, such that the compressor itself could now be characterized. With the vortex tube and the compressor modeled, analysis was finally done on the heat exchanger, accumulator, and refrigerated load.
Some important assumptions being made are the utilization of a lump mass model. Outside of the installation is an ambient temperature. The heat transfer rate due to ambient heating is negligible. The volumetric flow rate is not scaled to standard temperature and pressure. All the conversion functions are known with negligible uncertainty. All constants are assumed to have negligible uncertainty. Length and area measurements have negligible uncertainty, and the pressure drop across flow meters is also negligible.
The first experiment was run to experimentally characterize the vortex tube. This was done by analyzing the steady-state behavior of the vortex tube for different nominal pressures using the line pressures and no compressor. The first step is identifying the segments of data that are steady state. The graph on the left shows the pressure at station 3 versus the sample number. The steady-state segments are when the pressure evens out to the constant nominal pressure and are labeled on the graph. These are confident steady-state segments because there is little variation in the pressure within the segments. This plot shows the relationship between the steady-state temperature of the cold output of the vortex tube versus the pressure at station 3. A York regression analysis was conducted, and the regression equation is shown on the right. The conclusion from this analysis is that the temperature of station 3 cold output decreases as the pressure at station 3 increases. Here's the steady-state relationship between the hot output of the vortex tube versus the pressure at station 3. The York regression analysis shows a positive relationship between the two variables. This plot shows the steady-state relationship between the mass flow rate of the cold output of the vortex tube versus the pressure at station 3. The York regression shows a positive relationship between the two. Here is the steady-state relationship between the mass flow rate of the hot output of the vortex tube versus the pressure at station 3. The York regression shows a positive relationship between the two variables. With these trials run, the results were tabulated to be used in the refrigerated load steady-state analysis. The temperature at station 5 and the temperature of the load are also tabulated here because they are necessary for future calculations. The next experiment was run to experimentally characterize the motor and the compressor. This was done by analyzing the steady-state behavior of the motor and compressor for different nominal pressures generated using the compressor. First, the segments of data that are steady-state were identified. This graph shows the pressure at station 3 versus the sample number with the steady-state segment labeled. This graph shows the model of the steady-state relationship between the motor speed and the pressure at station 3. A York regression analysis was conducted and showed a positive relationship between the motor speed and the pressure at station 3. Finally, the results from the trials run with the compressor were tabulated as shown. This data is to be used in the heat exchanger and accumulator analysis. The total mass flow rate, shown in the rightmost column of the table, was calculated as the sum of the flow rates of the cold and hot outputs of the vortex tube.
Once the motor and compressor characterization was complete, the group moved on to analyzing the heat exchanger as well as the accumulator. Shown on the slide is the energy change rate plotted against the absolute pressure at point 3 in the system. As seen, The relationship between the energy change rate between stations 1 and 3 and the absolute pressure at station 3 is a linear relationship, and Q dot decreases as pressure increases. This shows that energy is removed by the heat exchanger before the air enters the vortex tube. The accumulator is also necessary because it steadies the pressure input to the vortex tube and maximizes the performance of this component. The next step in our analysis was looking at the refrigerated load. The first equation on the slide shows that the energy change rate of air is equal to the specific heat of air times the mass flow rate of the cold line times the change in temperature from station 4 cold to station 5. At steady state, our mass flow rate equals 0, so the energy change rate of air is equal to the energy change rate of the ambient air. The specific heat used was 1006 joules per kilogram Kelvin. Shown in the table is our data from the experimental dataset. With increasing nominal PSI, our Q dot air increased linearly. These values were then used to determine an R insulation value. This experimental value was derived from the equation in the top right of the slide. A theoretical value was also calculated based on the measurements of the insulation present in lab, as well as using a typical K insulation value of styrofoam, which was roughly equal to 0.033. The average experimental R insulation value was found to be 1.68 Kelvin seconds per joule, and our calculated R insulation value is 26.44. At this time, our group is unsure why the variance in these two values is so large, but next week will be used to dive into this value and further analyze whether our data accurately represents the model.
Thus, all of the steady state data was collected in the previous week from the building airline and the engine compressor system such that analysis could be performed. Energy transfer between the heat exchanger and the accumulator tank was calculated, and a value was found for the experimental thermal resistance of the styrofoam insulation. Next week, effort will be placed in modeling the transient cooling of the load by first the airline and then the engine compressor system. Once again, heat transfer will be analyzed to yield material properties. Concurrently, uncertainty analysis will be completed, and the validity of the system's ability to accurately represent the scenario will be checked. Finally, a report will be drafted to convey the findings and recommendations of the lab.